Ms. Victoria Gitman will talk on indestructible remarkable cardinals.
I'd like to start by thanking the organizers for inviting me. It's been a really great conference, and I am very nervous about spoiling your last impression of it. So that's one of the things that come with giving the last talk, so I'll try to do my best under the circumstances. Okay, so first to begin with, I will remind you of what remarkable cardinals are, or tell you about them if you maybe have not heard of them before. And to start with, this is joint work with Yong Cheng, who just got a position at Wuhan University in China. And so, as promised, let me tell you about remarkable cardinals. I'll spend about half of the talk describing their properties, because the definition is slightly more complicated than your usual large cardinal in very interesting ways. So, like any large cardinal, remarkable cardinals are defined in terms of the existence of certain elementary embeddings. But in this case, if kappa is a remarkable cardinal, the embeddings don't live in V, they live in the collapsed kappa forcing extension. So this is one complication. The other thing that's not what you would usually expect is if you have a large cardinal kappa, kappa is usually the critical point of the embedding. Here, if you look at the picture, kappa is the image of the critical point. And this may seem strange, but I will give, I think, a good motivation for it on the next slide. You will see that it's not as strange as it may initially seem. Okay, so let me tell you the definition with this background. So kappa is remarkable if in every collapse kappa forcing extension, for every regular lambda, there is an embedding from a small h lambda bar into h lambda. Small meaning that lambda bar is less than kappa. Lambda bar should be V regular, with critical point being sent to kappa. So you should think of it as no matter how big your h lambda is, there's a mini copy of it sitting below kappa. Okay, this is the characterization. This is the picture. I hope it helps. I worked very hard on these pictures. So why remarkable cardinals? How did they come up? What is their significance? So remarkable cardinals were introduced by Ralph Schindler. And Ralph, if I say anything wrong about the history, please feel free to correct me. And the question that motivated them was, so it was known that the assertion that the theory of Laver-like cannot be changed by all set forcing has consistency strength in the neighborhood of infinitely many wouldn't. So then the question was, what about the assertion the theory of Laver-like cannot be changed by proper forcing? And for a while, it was, it's obviously a weakening. For a while, it was considered that the strand would be around a strong cardinal. Some preliminary results suggested that this would be the case. But in fact, Ralph introduced this notion because it was precisely equiconsistent with this assertion. And it turned out that remarkable cardinals are nowhere near a strong cardinal. They are in fact consistent with L, so they're pretty small. And I will tell you exactly where they are in the large cardinal hierarchy in a bit. So the next thing, one thing I should point out before I go on. Because I'm always working in the collapse extension, whenever I say H lambda, I mean the H lambda of the ground model. If it's anything else, I would put a superscript on. So whenever you see an object without a superscript, it's a ground model object. So these are the H lambdas of the ground model. It looked very ugly if you put V on everything. So, okay, so here's my motivation to make the definition seem more reasonable to you of the embedding characterization. So Magidor, so I guess I should explain the title. You should think of remarkables, because of the theorem I'm about to state, as a generic version of supercompactness for the following reason. So Magidor showed that kappa is supercompact if for every regular lambda greater than kappa, there's an embedding J from H lambda bar into H lambda with lambda bar less than kappa and critical point mapping to kappa. And so remarkables have exactly the same property, only embeddings exist in the collapsed kappa extension. And it's very easy to prove Magidor's theorem, so it's not a deep result. You just think of the situation of H lambda, of restricting a supercompactness embedding to H lambda mapping into Hj of lambda and I, and reflect the situation down, and it gives you these kinds of embeddings. So that's the vague thing to say here. I want to give you another cute reformulation of remarkable cardinals as a generic large cardinal, not because it's useful, but because it looks pretty and it takes one slide. So I will do that on the next slide. As a preliminary, let me introduce the following lemma, which comes up in everything you do if you're working with remarkable cardinals. So the following lemma comes up in everything. And the gist of the lemma is the existence of countable embeddings is absolute between transitive models of set theory. More specifically, if you have a countable model and some embedding, so the countable model is M, you have an embedding J from M to N. M is countable, N can be any size you want. And it exists in V, and if you have some transitive submodel of V, not even of all of set theory, let's say of set theory without the power set axiom, so of some fragment of set theory, then if W, if the submodel W happens to have M and N as elements, and it knows that M is countable, it won't necessarily have J, but it will have an embedding from M to N. So the existence of countable embeddings is absolute for transitive models of set theory. And it's not, and moreover, you have this different J star, but you can preserve some key properties of the embedding J. So for example, if the critical point of J happened to be kappa bar, you can ensure that J star has the same critical point and it maps the critical point to the same value, and you can have agreement on finitely many values even. And this is very easy to prove. So you do the following. You construct a tree of all finite partial embeddings from M to N.
Is that fully elementary?
Yes. Yeah, these are fully elementary. All of my embeddings are going to be fully elementary. So you construct the tree of all finite partial embeddings. You can do this because M is countable. The tree is going to be the same no matter whether you construct it in V or in W. And this tree has the property that it has a branch if and only if there is an embedding from M to N. Well, we know that there is an embedding, therefore the tree is ill-founded, but this is absolute, and therefore you have now a branch in W and hence an embedding in W. And if you put restrictions on the tree, you will have these additional agreements with the critical point and everything else, and infinitely many values and some other things that you want to approximate. So this will come up a lot. This countable, this absoluteness of countable embeddings is going to come up a lot with remarkable cardinals. Okay, so here's the characterization that I want to give you. As I said, it's not very useful. I just like philosophically the way that it sounds. So here's an observation. Kappa is remarkable if for every regular lambda greater than kappa, there is a forcing extension that has an embedding J from H lambda bar to H lambda. Not necessarily a collapse, there's just a forcing extension that has the right kind of embedding. So different embeddings can exist in different extensions. A nice way to say it is there is an embedding somewhere in the, given the fixed lambda, there's an embedding somewhere in the generic multiverse. This seems much weaker than just saying that the embeddings have to exist in a collapse forcing extension. But in fact, it's equivalent. So I like that it's very easy to prove and it's pretty. So here's the proof. It will use the absoluteness lemma. So given an embedding in some V of H, I want to find an embedding in a collapse extension first. This might not sound sufficient, but let's just do first. So let's do this first. So suppose I have an embedding in some forcing extension. Let's get it into a collapse extension. Okay, so suppose I have an embedding in V of H. Let's force with collapse over V of H. So I've now formed V of H G. So here's my V of H G, and of course V of G is a submodel, right? And H lambda bar is countable in VG, and now you just apply the lemma and you get that VG must have a J star. But VG is a collapse extension. Okay, but it doesn't seem to suffice because I need to put all embeddings in a single collapse extension, right? And this was specific to forcing over V of H. But collapse is a very nice forcing. In particular, it is what is called weakly homogeneous, which means that certain automorphisms exist, which has the consequence that any statement about ground model objects, if it's true in one extension, must be true in all collapse extensions. So it means that if you have that P forces a statement about ground model names, then one already forces it. So this follows from weak homogeneity. So once I get it into a collapse extension, I now know that every collapse extension has it. And I'll use this property again. Okay, so this finishes my nice characterization, and now I have to talk about more characterizations, because somehow when I do the indestructibility arguments, I need to jump between these various characterizations to get what I want. It didn't work out as nicely as I thought it would. Okay, so just to make my life easier and your life more difficult, I'm going to introduce a definition that you will have to remember, but I'll have to write much less on my slides. So I don't want to say every time I have to say there is an embedding J from H lambda bar to H lambda such that kappa bar is the critical point and kappa bar gets mapped to kappa and then lambda and lambda bar are irregular. I don't want to write this every time. So I'm going to encompass this in a definition, and this is going to say now that the embedding is kappa bar kappa lambda remarkable. It just encompasses all those things, that the critical point is kappa bar, and then I'm mapping H lambda bar, and kappa bar goes to kappa, and H lambda bar maps into H lambda. Okay? And I have this mu here, and I need this more general definition, so instead of using kappa, which always think of it as kappa, I will sometimes need the more general definition. With mu here, it still means the same thing. So it means that this is the critical point, this is the image of the critical point, and these are the indices of the H's. Okay? So that's the definition. Now, let me give you the let me talk about an extended characterization. So we know we have these embeddings J, right? For every lambda, I have an embedding J. Would be nice if given an A in H lambda, I can put it into the image of a J, right? This is a useful property, and in fact, you have it. So there is not only one J, usually there are lots and lots of J's. Every A can be put into an image of such an embedding. An even stronger property is true, but I don't need the stronger property, so I don't state it. This is easier to state. One consequence of this in particular is you can have these J's with arbitrarily large critical points, because once you put an alpha less than kappa into the image, the critical point has to jump above it. So you can force arbitrarily large critical points. Okay, so this is one characterization to remember. Another is that given one of these embeddings, I can lift it to the forcing extension, which is sometimes useful because instead of now having an embedding into H lambda, I have an embedding into H lambda G, which is the H lambda of V of G. And this is just the lifting criterion. If you know what it is trivially satisfied. I will talk about the lifting criterion more later on. So if you don't know what it is, believe this for now, and I'll tell you later what the lifting criterion is. So I can always extend my embeddings to the forcing extension. Okay, those characterizations, the ones I just gave you, just extended the one that I initially gave you. Now here comes something that looks quite different. And if I'm not mistaken, what I'm about to state as a theorem was Ralph's original definition. Is this correct? And it's, I think Ralph has now switched to using the one I gave as the original definition as well. But this was the one that he first looked at, and it's not as attractive. What can you do? But it's extremely useful. I cannot make the indestructibility arguments work without it, and therefore I have to introduce it. So this one does not talk about collapse extension. Here all the embeddings are in the ground model. Everything here is in the ground model. So kappa is remarkably for every regular lambda greater than kappa. There are countable transitive models, M and N, and two embeddings. So I have an embedding from M into H lambda bar with some critical point that gets mapped to kappa. And I have an embedding from M to N with the same critical point. But now, so the height of M is a regular cardinal of N, and M is in fact H of that regular cardinal. And the critical point, so M sits inside of N, and the critical point has to go above M. This should look to you like an attempt to mimic the situation of H lambda bar and H lambda, because lambda bar is regular in H lambda. H lambda bar, of course, is the H lambda bar of H lambda, and the critical point gets mapped above it. So this is an attempt to mimic that situation. You should think of this as sort of a mini version of that. I will give you a practice with using this definition on the next slide, because we're going into now the large cardinal hierarchy. So I want to talk about where the remarkable cardinals sit in the large cardinal hierarchy. And first of all, I initially mentioned that it was conjectured that the strength of the assertion that the theory of Laver-like cannot be changed by proper forcing was around the strong cardinal. So you should not be surprised, because this was motivating the results, that the strong cardinals turn out to be remarkable. Which, think of it, initially is not really super easy to see. It's easy that supercompacts are remarkable. So let me give you a very quick argument using the definition on the previous slide, a sort of less intuitive definition, so we get a practice of working with it. So I have to produce, given a strong cardinal, and fixing a lambda, I have to produce Mn and the two embeddings, okay? All right, so let's fix a lambda strongness embedding. I'm using an M star here because I have the M for the other thing. So this is this weird, I realized it once I looked at the slides a third time that I have an M and an N. I had an M and that's not supposed to happen, so that's why the weird M star. I want it to be a lambda strongest embedding, so I have that H lambda is contained in M star and the critical point goes above lambda. Let's take J and restrict it to H lambda going, a mapping to J lambda of M star, and because of my assumption, H lambda actually sits inside Hj lambda. Therefore, this is a first order structure. The universe is Hj lambda. H lambda is a subset of it, J is a subset of it. And of course, the membership relation, take a countable substructure of this whole situation. So I have this X corresponds to the bigger one, Y to the smaller one, and then H corresponds to J. Collapse. Collapse X, get an N, the collapse of X is going to, the restriction of it is going to be precisely the collapse of Y because Y sits transitively inside X. And now I have, of course, the inverse of the collapse gives me a map of M into H lambda. Because of the properties, because it's an elementary substructure of this, I get all the right properties for this embedding. Because this has all the right properties, and therefore this does too. So that's why I was saying that you think that you should really think of the M and N as mimicking the situation with the H lambda sitting inside something. Okay, so strong cardinals are remarkable. Measurable cardinals are not necessarily remarkable. And the reason is, if you think about the definition of remarkables, and you know what totally indescribable cardinals are, it's easy to see that remarkables are totally indescribable. But a measurable cardinal is describable, so the least measurable cardinal cannot be remarkable. So you don't have an implication that way. The promise statement about L, here it is, very easy to see. In fact, remarkable cardinals are downward absolute to L. How do we show this? Well, given it suffices that if I have one of these remarkable embeddings to show that I can get it into L, right? Okay, so suppose that I have a remarkable embedding with all the right properties. This is a misprint. This should be kappa bar lambda bar. I always kept doing that. I can't remember my own definition, and I'm asking you to remember my own definition. Okay, so suppose you have one of those embeddings. Of course, you can restrict it to L lambda bar mapping into L lambda, but there is no reason to think this is in the collapse of V forcing extension. There's no reason to think that I can get it into a collapse L forcing extension unless you use the absoluteness lemma, which says that since L lambda bar is already countable, you have a J star. Again, this absoluteness lemma just magical. It gives you exactly the results that you want. And so, and again, it supposedly should be in every collapse extension. This is a specific collapse extension, but I have weak homogeneity. Okay? Okay, next. So you might be interested more specifically where the remarkable, so we know that the remarkable cardinals are in L, so they're one of the smaller large cardinals. You might want to know where more specifically they are. And so Ralph showed that they're weaker than an omega Erdos. And then I want to tell you a more precise bound, just because this lets me talk about my favorite cardinals, the α-iterable cardinals, because I introduced them. So this gives me a chance to advertise my α-iterable cardinals, so I'll take the chance. The official purpose is to give you a tighter bound of where the remarkable cardinals are in the hierarchy. So here's a quick crash course in α-iterable cardinals. Larger large cardinals are usually characterized by an embedding of the form J from V to M. Smaller large cardinals are usually characterized by embeddings of weak kappa models, of what I like to call weak kappa models. I don't know if it's standard terminology. And a weak kappa model is a transitive model M of ZFC without power set of size kappa and height above kappa. That's all that it is. So it's a transitive model of size kappa, and it has kappa as an element of an offset theory. Okay, so as I said, smaller large cardinals tend to be characterized by the existence of these kinds of embeddings. So M is a weak kappa model and can be big sometimes depending on the large cardinal, and of course with critical point kappa. And in the same way that if you have a J from V to M, you have a kappa complete measure. Here you have what is known as an M ultra filter. So if you use the definition that you would use to get a kappa complete measure, which is you use kappa as a seed, you will get what is called an M ultra filter. Why is it called an M ultrafilter? It only measures sets in M, and it's only normal for sequences from M. A formal way of saying it is that this structure satisfies that it's a normal ultrafilter. This U is usually external to M in most interesting cases, so it is not an element of M. And again, in the case of the large cardinals, you have an embedding J from V to M, an ultra power by a measure is well-founded if and only if the measure is countably complete. So this characterizes the well-foundedness. You have no such nice characterization for M ultrafilters. The best you can do is say this ugly thing. It's an M ultrafilter with a well-founded ultra power. So you have an embedding J from M to N if and only if you have an M ultrafilter with a well-founded ultra power. There's no nicer way to say it. Okay? Here's an example of a large cardinal that's characterized in this way, weak compacts. So kappa is weakly compact if 2 to the less than kappa is equal to kappa. We ignore this, although it is significant in applications. And every subset of kappa is contained in a weak kappa model for which there's an M ultrafilter with a well-founded ultra power. Equivalently, for which there's a J from M to N. Okay? So this is a definition. Weak compacts have the simplest definition in terms of these kinds of embeddings. Once you have ultrafilters, one of the things that you want to do is iterate the ultra power construction. This is what set theorists like to do. If you have a measure, if you have a countably complete measure, not only do you have that the ultra power is well-founded, all the iterates are well-founded. With these M ultrafilters, the situation is a complete mess. You can have the ultra power is well-founded, but, oh, I have to back up. I can't even iterate first. So with the M ultrafilters, I cannot even, because think of what you do when you iterate. When you do the successor stage, you take J of U, right? Well, you can't take J of U because U is not an element of your model. So you need some additional property on the ultrafilter to even be able to define the iteration, whether it's well-founded or not. And vaguely, this property says U is partially internal to M. It may not be an element, but it's partially internal. More precisely, the property is weak amenability. And it says that if you have an element of M of size less than or equal kappa in M, then its intersection with U has to be in M. So U is amenable, partially amenable to the structure that I had here. Okay. So this gives you the ability to iterate. You can now define the successor stage ultrafilter, but it does not guarantee any kind of well-founded. So as I started saying before, I forgot that I didn't tell you what weak amenability is. You can have the first iterate is well-founded, the second one is not. The first 7 are well-founded, the next one is not. The first omega plus omega is well-founded, the next one is not. So the situation is you can have arbitrarily much of the iteration being well-founded, and of course it stops at omega 1, because once you get past omega 1, everything else has to be well-founded. So this motivates the following definition of alpha-iterable cardinals. Think back to the weak compact definition. So I now say that kappa is alpha-iterable if every subset of kappa is contained in a weak kappa model for which there now exists a weakly amenable M ultrafilter. Before it was just an M ultrafilter in the weakly compact case, with alpha many iterated well-founded ultra powers. So that's why alpha-iterable. Okay? And they in fact form a hierarchy. So the more iterability you ask, the stronger the large cardinal notion, and they're all below Ramsey cardinals. So the hierarchy is bounded on top by Ramsey cardinals. So for instance, what does it mean to be one iterable? It just says that you have I did for every A, you can put it into an M with a weakly amenable ultrafilter where you have a well-founded ultra power. So the difference between weakly compact and one iterable is this weakly amenable assumption. That's all. But the difference in the consistency strength is really great. So here are weak compacts, here are ineffables, here are completely ineffables, which sit above a hierarchy of ineffables, and here's one iterable. So this innocent-looking assumption of weak amenability on the ultrafilter really pushes up your consistency strength. Okay, so
where unfoldables are in this power?
Here, between the weak compacts and ineffables, because subtle implies them. I think that's what it is. Okay, so me and Philip Welsh, who I'm happy is here, worked out the properties of this hierarchy And one of the things that we showed is where remarkable cardinals sit in this hierarchy. So they actually sit nicely in this hierarchy. And so remember, Ralph showed that they're weaker than an omega Erdos. It turns out that an omega Erdos implies, actually the alpha iterable hierarchy and the alpha Erdos hierarchy are completely intertwined. And an omega Erdos cardinal implies the consistency of a proper class of n iterables for a natural number n for every n. So it's much stronger than an n iterable for a natural number n. And so where do the remarkables fit into the picture? So a remarkable is one iterable, and it's a limit of one iterables. So a remarkable is stronger than a one iterable. But if you already have a two iterable, then there's a proper class of remarkables in V kappa. So they're really sandwiched very nicely between one iterable and two iterable. So that's my excuse for talking about the iterable cardinals. And that's it for the hierarchy. So we know precisely where they are in the hierarchy. This is the second part now with the indestructibility. Okay, before I start giving you lots of technical details, even if you miss everything that follows, the general impression that you should take away is that indestructibility properties of remarkables are those of strong cardinals, basically. So they're very similar to strong cardinals. And in order to prove them, you need to figure out the analogs of everything that strong cardinals have in the remarkable case. This is the strategy of the proof. Once we had that figured out, everything else worked out very easily by just using techniques from the strong cardinals case. And one thing that strong cardinals have are Laver-like functions. And this was crucial for the argument. So let me remind people about Laver-like functions. They're very useful, in particular. They're of inherent interest for themselves, but they're mainly used in indestructibility arguments. So suppose kappa is a large cardinal characterized by some type of elementary embeddings. A Laver-like function I use the three dot notation Hankins style to denote that it's a partial function, okay? So three dots means partial function. So it's a partial function from kappa into V kappa, and it's a guessing function. Think of diamond. So this is supposed to be a generalization of diamond in the setting of large cardinals. So for every set A in the universe, there's some J of the type characterizing the cardinal such that J of L of kappa is A. So it guesses A with some embedding, okay? So let me give you the template for what a Laver-like function would look like for some large cardinals. And then on the next slide, it will tell you for which of them it actually exists. So this is just the definitions, right? So for a supercompact, more precisely, you would ask that for every A in H theta, there's a theta supercompactness embedding J with J of L of kappa equals A. And of course, as the name suggests, Laver first introduced Laver functions in the context of a supercompact in his indestructibility result. For strongs, it would be for every A in V theta, there is a theta strongness embedding J such that J of L of kappa is equal A, the same template. For extendibles, you would have for every A in V alpha, if you know the definition of extendibles, there's a J from a V alpha to V beta with J of L of kappa equals A. So far I've given you three very large cardinals. You can also define Laver functions for Laver-like functions for smaller large cardinals. So Joel mentioned unfoldables, which is very good because I was just about to talk about Laver functions for strongly unfoldable cardinals. So what's the definition of a strongly unfoldable cardinal? So it says that every A subset of kappa can be put into a V kappa model such that you have a J from M to N, so A is in M. But now N is big. It contains V theta. You should think of them as mini strongs. So that's what a strongly unfoldable is, and the definition is exactly, the template is exactly the same. So it doesn't matter whether it's a large cardinal or a smaller large cardinal, the template is the same. Often you want these useful additional properties on the Laver functions. You want the domain to be contained in the inaccessibles, and you want every point to be the closure point of the function. This is useful in indestructibility arguments, and it usually comes free once you've defined the Laver-like function. Okay, so those were just definitions, right? Now I can tell you which cardinals, give some examples of which cardinals have them. The general story is you can force them for most large cardinals, but very few have them outright. So it's very nice with a new cardinal, when you discover a new cardinal that has a Laver function, a Laver-like function outright. So of course, Laver showed that every supercompact has a Laver function. Gitman and Shalai in their paper and the Gitman indestructibility for strong cardinals showed that every strong has a Laver-like function. Corazza showed that every extendable has a Laver-like function, and Hemkins and Jamonia showed a negative result that not every strongly unfoldable has a Laver-like function. So this is one of the examples of a cardinal which doesn't. So the smaller large cardinal. And so the first thing when we were looking, as I said, at the indestructibility properties of remarkable cardinals, we realized unless we had a Laver function, nothing was going to work. So it was somehow, if we wanted to generalize the arguments from Strong's, we needed a Laver-like function. And it turns out that remarkable cardinals do have a Laver-like function, which I really liked. But the situation, again, because of the strangeness of the embeddings involved, it's not even easy to figure out which one the Laver-like function to be. Because think of what it was in the template, J of L of kappa. Well, L is a function from kappa into V kappa. For these embeddings, it doesn't make sense to apply J to L. L is too big, so you cannot do it. You cannot use the standard template. You have to make some modification in order to make the definition work for remarkable cardinals to have the property that you want. And the solution is kind of obvious. Don't apply it to L, apply it to a sufficiently large piece of L to get kappa into the range, into the domain, to get kappa into the domain. So instead of saying that J of L of kappa is equal to A, what we say is, okay, we need this piece, first of all, to be in H lambda bar. So I want L, the minimal possible piece is L kappa bar restricted to 1. L restricted to kappa bar plus 1. This is the smallest possible piece where this makes sense. I can apply the image to kappa. So I want it to be in H lambda. I want kappa bar to be in the domain, otherwise this won't work. And then A should be J of this piece of L evaluated at kappa. And there's this equivalence. So in this case, this is simply J of L of kappa bar. Okay? So here's the picture. So I have, and the one property that's very useful in the arguments is kind of intuitively the thing you want. You want this little piece of L to actually map up to the whole L, and you get it. Okay, so here's the picture. This little piece of L here that exists in H lambda bar gets mapped to L. L of kappa bar is the thing that guesses A. Okay, so this is the picture that we have, and I get the usual properties, the usual additional properties that you want. Okay, I want to give an argument because it's kind of, it's not very difficult to show that, to prove that remarkable Laver functions exist. The argument is just in the same way that Laver's argument mimics the diamond argument. In the same way, this just follows Laver's argument. The idea is always the same. Build inductively, put on the sequence the least counterexample to the guessing property, right? This is always your idea. So this is exactly these technical looking definitions. Keep in mind, this is just what I want to do. I want to define what it means to be a least counterexample, and then I want to include it in the definition of put it on your sequence. Okay, so this is what this is saying. So let's make a definition. Suppose I have, think of this L mapping Xi to V kappa as an initial segment that I constructed, and now I want to define L of Xi, okay? So suppose I have this L so far on Xi. Let's say that X is lambda anticipated. If I have a remarkable embedding, but not with critical point, because I'm now looking at this reflection to Xi, right? So my critical point is no longer kappa bar going to kappa, it's now Xi bar going to Xi. Okay, this is the same as in the diamond case, the same as in the Laver function case. Okay, so let's say that it's lambda anticipated if there's an embedding which anticipates it. And otherwise, it's not lambda anticipated. And so I will want to make L of Xi be the least thing that's not lambda anticipated for the least lambda. Now, it's really important because the function should map into V kappa that the least such lambda be less than kappa. Otherwise, the whole thing breaks down. So the key lemma is precisely this. If something's not lambda anticipated, the least one is below kappa. Worked out very nicely, use the absoluteness lemma, not a difficult proof. Everything here uses the absoluteness lemma hidden in somewhere, so that I can always bring things down to a smaller structure. Okay, so now in the definition there's this very annoying thing is I need to fix a well ordering of v kappa in order to pick the least counterexample. But you basically fix it once and forget about it, never think about it again, but you know you have to in some arguments be careful to make sure that this w is around. But we use it and forget about it. In the paper I actually have L of w, like indices and everything to make the details precise, but it's not terribly significant. So I define it exactly the way that I just said. Suppose that you've defined it up to c. Check if something is not lambda anticipated for some lambda. Pick the least one, let it be lambda prime. We know it's below kappa, so I can use w to pick the least counterexample, put it on the sequence. That's my definition. And the next slide says that this actually works. Oh, I should have noted something. Look where I'm working. I am not working in V. I'm defining this L in V of G. Everything here it says in V of G, work in V of G, make this definition in V of G. So this kind of seems to be bad because I want my Laver-like function not in some V of G, maybe two V of G's actually define it differently. I want it in L. I want it in V, in the ground model. But it turns out we have this weak homogeneity property for collapse, and I'm going to use it again. Because the definition of L involves only ground model objects, so it talks about there exists an embedding from between ground model objects. In fact, if something is true, it's already forced by one. So it's very easy to see that in fact the definition is independent of the collapse forcing extension in which you work. And in fact, I could have written here, instead of saying in V of G, I could have said one forces, and I get exactly the same thing. Because of this property, I'm never saying what the embedding is. I'm always saying there exists an embedding, and therefore the statement is only about ground model objects, namely the VH is involved. Namely the H is involved. Okay, so I kind of cheated. I defined it in V of G, but in fact the object, I could have just written one the way I do in the paper, but the statement looks incredibly ugly and unintuitive. So, and you can, in fact, if you define it in V of G, you get the same object. So, and it's always all the arguments themselves are in V of G. Okay, so I have this L, I defined it in V of G, but in fact it's easy to argue that it's independent of the extension and the object itself exists in V. This worried me for a while until I realized that of course weak homogeneity gives you that it must be the same everywhere. Because if it's in V of G, it's not very useful in indestructibility arguments. Okay, so quick sketch of a proof that there is a remarkable Laver function. This just mimics Laver's argument in the context of remarkables. So it's the same recipe exactly. So let me do that. Well, what does it mean that L is not a remarkable Laver function? It means that that sum A is not lambda anticipated using this definition, is not lambda anticipated by L, okay? Well, let's assume sum A is not lambda anticipated, and let's get a contradiction. So suppose sum A is not lambda anticipated, and let lambda be the least such. I can always pick the least lambda for which something is not lambda anticipated, and fix a large enough tau, h tau g that it sees this situation. Okay? Well, I have remarkable embeddings for everything. In particular, let's find one from h tau bar into h tau and lift it up. Okay? And lambda is definable because it's least, so it has a preimage. Let's call it lambda bar. It didn't matter. I could have put it in the range anyway, but it's definable, so I don't even have to worry about it. I have this property that J of L restricted to kappa bar is L, and this needs this annoying W is in the range of J, but I can put anything into the range of J, so it's all in the details. Okay, so far I have this which witnesses that L doesn't work, supposedly. I fixed a remarkable embedding. I now want to reflect this property that L doesn't work down. And so by elementarity, the smaller structure now thinks that lambda bar is least, such that some x is not lambda bar anticipated. Therefore, in particular, and it must be correct about this, which is key. So it thinks it's correct. This needs absoluteness lemma. You think about it for a few minutes, you see why. Okay, so I have that some element is not lambda bar anticipated, and lambda bar is least, therefore I know exactly what L kappa bar is. It's defined, because by definition, if something is not anticipated, I take the least thing. It's something that's not lambda bar anticipated, and this should be, do I care? No. Okay, so this is something that's not lambda bar anticipated. So now, before I push down using elementarity, now push up using elementarity. So by elementarity, from this it follows that J of L J of L applied to kappa gives you something that's not lambda anticipated, because the other thing was not lambda bar anticipated, right? Remember, no, I don't want to be here. Wait, why do I want to be? Why did I do that? Okay, hold on. Oh, because I wanted to press this. Okay. So remember, this is just J of L kappa bar, right? So it just by elementarity, this is not lambda anticipated because the other one was not lambda bar anticipated. I invite some element. I don't care what it is. I just care that something is not lambda anticipated, okay? And this has this form. But this is obviously lambda anticipated from the point of view of this structure. Namely, it's lambda anticipated by the restriction of the embedding that's big enough to have this property. So in the supercompactness case, if you know the argument, you actually have to find a factor embedding that witnesses the lambda anticipation. But here it's even easier. You just take the restriction and it already gives you everything. That's the contradiction. Therefore, your initial assumption was wrong.
Yeah.
Yes?
Why do you need leastness? And why do you need to introduce this well order to get leastness?
Because how else do I pick the least thing that's not anticipated?
Don't demand that it's least. Just pick one that's not anticipated and.
No, but you have to somehow pick. You have to use.
Choice function.
Yes, you have to. You're using something. I couldn't get rid of this W number. It annoyed me. It plays no significant role anywhere. Other than you have to carry it around with you all the time. If you can help me to get rid of it, if you think about it and help me to get rid of it, I would like to. I could not do it, and it's maybe possible. I don't know.
It's in Laver's argument too. I mean, he picks the least one.
Yeah.
You just pick one, any one, but it's
Yeah.
a choice function, so there's really a well order.
I think people just sweep this under the rug, basically. And I somehow couldn't because I was worried about the details, that I was missing something somewhere. So I tried to write down the most explicit possible thing. Okay, I want to get to the actual indestructibility argument, so let me say one last thing about. So we now know that there is a remarkable Laver function, and now I should tell you why we care that there is a remarkable Laver function. Well, I like Laver functions in general. But the main reason that you care in this context is Laver-like functions give you, if you're defining a forcing iteration, and you define it for things and you do non-trivial forcing only for things that are in the domain of a Laver-like function, you get gaps where the forcing is trivial, and those gaps help you with lifting arguments. So the purpose of a Laver-like function is to create gaps. Okay. So this is what this theorem is saying. This is what this lemma is saying. It's saying that I can always find an embedding, I can always find a remarkable embedding J from H lambda bar to H lambda, such that from kappa bar up to lambda bar, I have a gap in the domain of the Laver function. At the same time, I can make the Laver function guess whatever I want on one of the, basically guess whatever I want. So the Laver function does two things. It guesses what I want and it gives me a gap. The way that you create gaps is that you use the property that every point is a closure point. If you want to create a gap, you just push something out of the interval, right? If you want to create a gap beyond lambda bar, you just push the next value to lambda bar plus 1. So you just make, if you want the gap, you just make, this should have been J of L restricted too. You just make J of L of kappa on the second coordinate here, make it big enough that you get out of H lambda, out of V lambda, so back by reflection you will be out of V lambda bar and you have your gap. So you use the closure point property that you always get free once you have a remarkable Laver function. And I will use the guessing property in a moment. Okay. So what is the strategy for showing indestructibility for remarkable cardinals. It's the usual strategy, lift embeddings. You have embeddings, find lifts and that verifies the property in the forcing extension. In the particular context of remarkable cardinals, I have two embeddings. So I have an embedding from M into H lambda, this pi that will need to be lifted, and then I have sigma from M to N that's going to need to be lifted, in such a way that I preserve the properties that they had before. Here, nothing much needs to be done. I just need to lift. Of course, this will only work for the partial orders where H lambda G is H lambda of V of G, right? This doesn't work in the other case, but in most interesting things, this is the case. I mean, it will be the case high enough up, right, for any forcing, above the forcing. The key thing is lifting. You really have to be careful to lift sigma, because when you lift, you need to preserve that the height of M is still regular in the forcing extension, and also that the forcing extension of M is still H of the height. The gap in the Laver function will do that for you. So that's what the gap in the Laver function is designed to do, to preserve those two properties. It shows that once you have this, you cannot ruin it after the closure of the forcing kicks in. Okay? And now how am I going to find these generics that I need? I'm going to use what's usually used, the lifting criterion, which says that if you have an embedding J from M to N, and you want, so here the poset is M, and here the poset is P, and here it's J of P. So if you want to lift, and you already have a generic for P, you need to find a generic for J of P that contains the image of G. This is the standard technique in indestructibility arguments.
Okay, it's not quite stated correctly.
What did I do?
You have, if you really want, if and only if you have to say, you have to add H equals J of G. Because otherwise H could be totally unrelated.
You're right.
I mean, if there's some, if
You're
it's
right.
homogeneous or something,
You're
you
right.
have a different
You're
H,
right.
so lift the embedding, but you wouldn't.
You're right.
Like there's some
You're right.
equivalent H.
Yes. You're right. You're right. Okay, so the key slide is this. After this slide, I can just wave my hands and tell you how the indestructibility argument goes, because I won't have time for anything else. So the key to these indestructibility arguments is to find embeddings that mimic the property of extender embeddings of strong cardinals. Because once you do that, you can just directly apply the strong cardinals techniques. Okay, so I don't just want any pi and sigma, I want good pi and sigma. And good pi and sigma are kind of a little difficult to get, but I'll try to, I mean, they're not difficult to get, they were difficult to figure out what they are. But once you figure it out, everything works. So here's how I get a good pi and sigma, given that I have some pi and sigma, okay? So let's fix a regular lambda, and I want a good pi and sigma for this lambda, right? Now, first, I go way above lambda to some delta. And I fix some embedding rho from a countable structure into H delta. Remember, delta is this thing way above lambda, okay? I always have them. I just take a countable substructure, I collapse it, and rho is the inverse of the collapse, right? So I always have these things. And put everything you need into the range. Make sure that kappa is in the range, lambda is in the range, the Laver function's in the range, throw everything in and more. And now I do a trick. So M prime is a countable model. And I know because M prime has an elementary embedding into H delta. H delta knows that for lambda there must be it knows that for lambda, in any collapsed extension of H delta, there must be remarkable embeddings. Therefore, M prime knows that in any of its collapse extension, there must be remarkable embeddings for lambda prime, the preimage. So I go to a collapse extension of M prime. And I fix a generic for it because it's a countable structure. I have lots of generics around, pick one. And now what does this collapse extension has? It has what it thinks is a remarkable embedding from some small h lambda bar into its h lambda. Let's look at the picture, what is going. So I have this big h delta. I have M prime mapping into h delta I, and it sends lambda prime to lambda. In particular, one of the pi's that I can use is I can just restrict rho to h lambda prime, because that maps into h lambda. So I can make this little thing my m, okay? I'm not going to, because it doesn't work. So I could have made this my m, but it's not yet what I want. Instead, I work in the collapse extension of this, and I obtain an embedding from some h lambda bar into this little structure that I didn't want to take as my m, okay? Don't look at this yet. So far, I have in the collapse extension, this is really, I mean, it's sort of messy, but it's the only thing that works. So I have this big one. I could have taken this as my m. Instead, I'm going to take the smaller thing as my m, because I have an embedding from here to here and then from here to here. So this does have an elementary embedding into h lambda. Why do I want to take this instead of this? Because since this looks like a remarkable embedding, and I have a preimage of a Laver function, for this one, so don't look at this one yet. For this j, I have that this big thing has what it thinks is a remarkable Laver function with a gap for this, okay? And this is crucial for the indestructibility arguments. So I could now, I have an m and I have an embedding into this, and a very natural n is this, because I just said it has a remarkable Laver function and a gap and everything, but I don't take it. So my m is now correct, but this is not my n. My n is the factor embedding that I obtain from j. This structure is too big. My indestructibility arguments don't work with it. Instead, I have to take the usual factor embedding. And that factor embedding looks like an extender, and now this looks like an extender embedding. It has all the required properties, because this one did, and the critical point is high enough to preserve it. But this one looks like an extender embedding. And therefore, I will be able to use techniques which work with strong cardinals. So now, what are the good pi and sigma? So the good pi and, yes. So the good pi is the composition of this and this, and then the good sigma is this, okay? The extender, the thing that mimics an extender embedding. And now I can just quickly tell you what the indestructibility results are. We have two, which we then combine into a single general result. One is that a remarkable cardinal can be made indestructible by at kappa theta simultaneously for every theta. I'm not going to go into the details. I have all the details written out, but the basic idea is this: use Wooden's surgery argument. Because we managed to get what looks like an extender embedding, Wooden's surgery argument will work. And if anybody has any questions, and if we have time in the question session, I can answer them. So the details are basically, it comes down, there are a bunch of technical details, but it comes down to surgery. So you use Wooden's surgery argument. Okay, because everything, the really crucial thing was the previous slide with the good pi and sigma. Once you have it, I just do strongness techniques. So you get the preservation of the properties because of the gap with the Laver function. You get that surgery works because you have an extender. You have to do one trick to lift the pi embedding. But the way that you do that is you use that you have a countably closed forcing. So the preparatory forcing to make something indestructible by at kappa theta is countably closed, which means that it is proper, and the properness is used to lift the first embedding. This is also sort of a weird trick there. The second thing that you can get is indestructibility. Okay, so what I really wanted to get, I don't know how to block this out. Well, initially, we thought we had that a remarkable kappa is indestructible by all less than or equal kappa distributive forcing. And then we noticed the gap. That's what we wanted, but didn't work out. You need less than kappa closed, less than or equal kappa distributive, which looks really ugly. But luckily gives the applications that we wanted. So it didn't ruin the applications. Once we saw that, we were like, oh, okay, once you have the application, it doesn't really matter that it looks ugly. Without closure, I don't know how to do it. Here you use, again, just strongness techniques, okay? And so the combined result is that you can put the two arguments together to get that there is a remarkable, that every remarkable can be made indestructible by all less than or equal kappa distributive, plus forcing of the form at kappa theta followed by a less than or equal kappa distributive. And it's the second one, so things of this form, iterations of this form, that give me the applications that we were interested in. So finally, what are the applications? One thing you can do now is you can show that any consistent continuum pattern on the regulus above a remarkable works. When I say consistent, I mean throw in the usual restrictions. That has to be via Koenig's inequality and all that. So any continuum pattern above a remarkable cardinal works. If you want to talk about below remarkable cardinal, which continuum patterns work, this would be, I want to look at it at some point to see if I can mimic the result from supercompacts. I don't remember who it was due to Menas, maybe, I think. He has a result for supercompacts, which one can try to generalize, but it's very easy to get a pattern above a remarkable. The other thing is, so we know remarkables are downward absolute to L. A natural question is, are remarkables in general downward absolute to transitive models, to say inner models of set theory? And the answer is no. Using techniques recently developed by Joel Tsai and my collaborator here, Yong Cheng, with the indestructibility that we have, we can show that there's a remarkable which is not even weakly compact and hard. So our remarkables are not downward absolute to hard, and this goes on the list of Joel Tsai in this project of cardinals which lose their large cardinal property which can lose their large cardinal property once you go down to hard. Okay.
So your main indestructibility result where you have less than kappa close plus less than or equal kappa distributive, I mean, it looks a lot like the Gittic-Shala indestructibility, like the first part of the Gittic-Shala indestructibility for strong cardinals, except then they went on to consider this more general thing of forcing with the Pickry property and a generalized Pickry property. And so can you, do you have ambition to that also? Or?
I looked at it briefly, and my conjecture is that it will work. All the techniques are already in place, so this is one of the things I plan to look at in the next few months. I think that because of these good sigma and pi, once that is there, I think everything else is just going to go through precisely as in that case. So I'm very optimistic that you will get Gittic-Shala indestructibility for remarkable cardinals.
Yeah. Thanks very much for that. So the characterization of remarkability you're working with there has an equivalent formulation just using kind of objects intra V. You don't have to characterize it in terms of the extension. Are there sort of similar notions in this area where there's no known formulation from within V?
I mean, of course, the generic large cardinals in general, right? So this, it has a flavor. It's not a real generic large cardinals the way that they're usually defined, but it has this flavor of the philosophical idea of generic large cardinals. So, and there is not, actually there are ways, so a remarkable cardinal is in this sense a generic supercompact, in the sense that the embeddings exist in a collapse extension. And you can actually do this with other large cardinals, and me and Ralph have started looking at that. What kind of large cardinal notions do you get, but starting instead of supercompact with some other large cardinal. So this would give you a zoo of these generic large cardinals that mimic the properties of the large cardinals.
Cool, thanks.
Other questions? Not the case. So let us thank Victoria and before I hand over to the president, let me